The solutions, module 7, page 283, questions 1 to 4. These involve your entities calculation as well as your mole calculation. So just be careful to know which formula you're going to be using. So I'm going to write them at the top. Our entities formula looks like this, where N stands for entities. It could be molecules, atoms, whatever they ask you for in the question. N equals moles. And Na, we already always have, it's a constant, 6.02 times 10 to the 23. That is Avogadro's numbers. So if it was in molecules, it'd be the amount of molecules in 1 mole. And of course, moles equals mass over molar mass is our other one. Question 1 says calculate the number of molecules present in each of the following samples. So pretty straightforward. This is just going to be a plug and chug, but I do recommend you always write down what you know. So we know we have 2 moles of ammonia, and of course, we always know Avogadro's number. So at this point, and it would be entities per mole, we're calculating molecules. So there are 6.02 times 10 to the 23 molecules in 1 mole of ammonia. So now you just have to insert numbers accordingly. Multiply. To get molecules on their own. Because there are that many molecules in 1 mole. So again, you're dividing out for unit analysis. And I have previously calculated this to be 1.204 times 10 to the 24 molecules of ammonia. Now again, I can critically analyze my answer to say that instead of having 1 mole, I've got 2, so the number has to be bigger than what I started with, and it was. I just realized that I misread this question, so that's okay. We have to do a little bit of extra work. This one gives us mass, and it's in milligrams. So we need to then change it to grams. And all you're going to do is move the decimal 3 places because we are dividing by 1,000. So it ends up being 0.0016 grams of water. We're trying to get to molecules, so it's a 2-step process. The unit that connects the 2 of these is the mole. We don't know how many moles we have in that 0.0016 gram sample of H2O, so we still have to calculate that, but of course, we can always find molar mass of H2O. So H is going to be 2 times 1.0079, and then O, of course, is 15.999 grams per mole. And again, I'm getting in a bad habit of not writing in the units. It's a do as I say, not as I do. And we have learned that when you multiply and then add these together, it's going to be something like 18.01 or 18.02. So I'm kind of taking a shortcut here because I didn't previously do this calculation. I have in other videos. And then it's a straight plug and chug using moles equals mass over molar mass. I've already done the unit analysis as well before, so I'm not going to show that again. I just want to double check my math here. So it's a tiny amount of grams, so it's going to be a tiny amount of moles as well. I think that's 4 zeros. That's why I kind of like scientific notation better. So I don't have to continually double check and count the zeros. And so now I have the number of moles. We know that the number of moles, or sorry, moles as a unit, is connected to both of these equations, in that it also occurs in the entity equation. So if I want to figure out the number of molecules present, well, I can take the number of moles and use my Avogadro's constant to figure out molecules. So I am just going to change this to scientific note. Well, I have it in my calculator already, so I guess I'll just... So remember, in the multi-step calculations, you should carry all your decimals to the end, as painstaking as it is. And I forgot to write moles. And this is going to multiply by 6.02 times 10 to the 23. Again, this is molecules, the number of molecules in 1 mole. So that cancels. And I just happen to keep the numbers on my calculator so I didn't have to keep writing them out. So I know because I'm multiplying it by a really small decimal, my final answer is going to be smaller than the original Avogadro's number, which it is. And my calculator finally said, nope, I want it in scientific notation because it's too many decimals to carry. So this is what I ended up with. You might have a different number of decimals there. Okay, so question 2 is fairly similar in that it's asking for atoms, molecules, and then grams. You really need to, as I mentioned before, get in the habit of writing down all of what you have in the question so then you can identify what you need in your final answer. So 2A gives me atoms. So that is big N. That is the number of entities. The entity happens to be an atom. I have a 3.01 times 10 to the 23 amount of atoms of copper. And it says calculate the amount. So remember, amount in your book means moles. So we don't know moles. So of course, we're going to use this equation here. I'm going to get rid of that little... And again, I like to rearrange before I plug in chug. So I need to isolate for moles here. So I'm going to then multiply both sides, or sorry, divide out by both sides by Na. So that gets rid of that. And then divide it over here as well. And I'm left with moles equals entities over Avogadro's number, which we know we always have. It's a constant. And in this case, I'm describing atoms. The amount of atoms in 1 mole of copper. So I can straight plug and chug to get rid of atoms. And I can critically analyze this answer and know that it's a smaller answer on top, a larger answer on the bottom. So it's going to be less than 1, and we are left with moles. Because it's atoms divided by atoms per mole, which is a fraction. So remember, when we're dividing a denominator, a fraction in the denominator, you have to flip and multiply. And that will cancel your atoms. So now we have molecules of hydrogen chloride in hydrochloric acid. This one's pretty straightforward as well, only the entities are molecules and we're trying to get to moles. So it's just a straight plug and chug as we did before. Oh, this is to 25. I'm like, well, we know what that answer is. It's going to be 1. But in the question, it's 25 molecules. So it's the same calculation as atoms, remember. And that is the number of molecules in 1 mole. So once we do the unit analysis there, we are left with, oh yes, I could have done that in my head. 100. I know, because it's the same base. So with the scientific notation, when you have the same base and you're dividing, you subtract those two, which means it's 10 to the 2, which is 100. So you have 100 moles, sorry, of HCl. All right. And then C, this is where we're going to have to do a multi-step calculation again, because we're given grams of CaCO3. So write down what you know. We know that our mass equals 42 grams. We don't have moles. We do have molar mass, or we can calculate it. From my periodic table, calcium, the molar mass is 40.078. Carbon. And then oxygen is 3 times 15.9. So again, I'm not going to show that multiplication. I'm just going to get the final molar mass of this thing, which is 100.086 grams per mole of CaCO3. So that is going to be a straight plug and chug. That is the equation on the right. Moles equals mass over molar mass, which then equals 42. And all of that just to get to the number of moles, which is and just for ease, I'm going to round to, oh, that's actually what they want. So no multi-step calculation needed, because 2C, I'm getting tired here, 2C asks for the amount of the substance in each of the following. So we did find the amount of moles because your book wants moles. And so you needed to use your mass and your molar mass. Let's take a look at 3 and 4. It says a sample of carbon dioxide contains 4.2 times 10 to the 24 molecules. How many atoms of carbon and how many atoms of oxygen are in the sample? Well, that just goes right back to your covalent naming. We know that carbon dioxide and its covalent formula is CO2. So A is straightforward. How many atoms of carbon are there? Well, there's 1 atom. It shows you right in the formula, which means that there are 2 oxygens. So we can describe that as being 2 atoms of oxygen in that carbon dioxide formula. So very, very straightforward for just calculating CO2 on its own. The problem, though, is the sample of carbon dioxide in 3 contains 4.2 times 10 to the 24 molecules. So I'm going to write N equaling 4.2 times 10 to the 24 molecules. So we need to determine, though, because it wants to know how many atoms of carbon and how many atoms of oxygen are there in the sample. We have to take into account all of these molecules. So for question 3, CO2 equals, it is 1 molecule. In 1 molecule, you have 1 atom of carbon and 2 atoms of oxygen. But we don't have just 1 molecule in the sample. We have 4.2 times 10 to the 24. So I would then calculate the atoms for carbon in the sample and the atoms for oxygen. And all you have to do is multiply that by how many in 1 molecule. So for carbon, it's going to be 4.2 times 10 to the 24 molecules. And carbon only has 1 atom in the molecule, in 1 molecule. So that means that, because that's 1 atom per molecule. So unit analysis cancels out, and I have 4.2 times 10 to the 24 carbon atoms. But if I'm calculating oxygen in my 4.2 times 10 to the 24 molecules, well, in 1 molecule of carbon dioxide, I've got 2 atoms of O2 per molecule. And for some reason, I didn't calculate that already. Guess I could have done that in my head as well. 8.4 times 10 to the 24 oxygen atoms in the sample. Now, if I wanted to get the total atoms in the sample, it doesn't ask you for that. You would have to add that amount together to get the total atoms in 4.2 molecules. It says, what is the mass of the sample? This is where it's a multi-step calculation because we don't have enough information to go right to mass. We can calculate molar mass of carbon dioxide, but we still are missing moles. So the total molar mass of CO2 we don't know moles. We do know atoms though, we know molecules. And we always know Avogadro's number. So you're going to be using both of the equations up at the top. And I like to rearrange first. So N equals N times Na. And you don't have to. You could have put the numbers in and then moved the numbers in if you wanted. And remember, these are in molecules per mole, and then we know there's molecules in 1 mole, so that becomes 6.976. So I have to take that number and plug it into the other formula, moles equals mass over molar mass, to find the mass. So this is almost step 2 here. So now we do have the moles. And we previously calculated the molar mass to be 44. So the units cancel to leave us with grams. So our mass is going to equal 307.04 grams. And then question 4, sodium hypochlorite is the active ingredient in chlorine bleaches. A sample of chlorine bleach contains 120 grams of sodium hypochlorite. So how many formula units are in the sample? So remember, formula units just tell us essentially the lowest whole number ratio of the sample, which is in fact our ionic formula already. So sodium hypochlorite is an ionic compound. It's a metal and a polyatomic ion. And we describe that in formula units, as I talked about in class. I would write down what you know, which is the mass. Our molar mass we can always calculate. Doing better to install these units. So your molar mass here becomes 74.442. And then from here we can calculate moles by plugging it into the equation above. And I get 1.611999323 moles, which I can critically analyze my answer and know that that is approximately right. And then we need to do step 2, where we move to formula units, which is our entity. So we don't know what our entities are. We have moles and we have Avogadro's number. And that would be the amount of formula units per mole. And so it's just a plug and chug from that. Because remember, 6.02 form units per mole will give us the final answer of 9.70, and I rounded already, times 10 to the 23 formula units. So you had to go through a few steps to get to that final answer.